Okay, hello everyone, and welcome to the Population Dynamics and Health Program workshop. For today, my name is Paul Schultz. I'm a statistician and data scientist here for the Center, the Population Dynamics and Health Program. We're located here at the University of Michigan in Ann Arbor, Michigan. For those of you who are dialing in from abroad, welcome. I just want to take a couple minutes today. I know that our time is always precious in these workshops, and really especially so today. We've got a ton of content that we're hoping to get through in 4 hours, so I will keep this short. I know you're not here to hear me talk, but just wanted to welcome everyone here today. Again, this workshop's hosted by the Population Dynamics and Health Program. We are sponsored by the National Institute of Child Health and Human Development, so I want to take a minute to thank our funders. We're also co-hosted today by the Network on Life Course Health Dynamics and Disparities, which is NIA funded and is also co-led by the Population Studies Center Director, Sarah Burgard, who works with me here in Ann Arbor. So wanted to thank them again for co-hosting this workshop. I wanted to take just a minute to introduce our center. I'll keep this short. I mean, I'm purposely going to gloss over a lot of the details. This is this applied multi-level models workshop. I know is a wide-ranging topic, and so a lot of you may or may not be population researchers. But for those of you that are population researchers, I just want to point out I've got our website up here. We support population research here with our team. So I help manage a team of data scientists and statisticians, basically technicians that can help you with any aspect of your research. And so we've got an affiliate program here that unlocks some things that you might be interested in, such as a small grants program and also free consulting with myself, my team, and Brady West as well. And so, that's open to any affiliate of our center. Again, I won't walk you through that. You've touched the website if you've RSVP'd for the workshop. So I'll just refer you back to our website, but just be aware that there is some more things that we do besides the workshops themselves. And I just encourage you to hit our website or contact me directly if you do population research and you're interested in any of those features. The website's here on screen. It's pdhp.isr.umich.edu. Another thing I wanted to mention, we offer a coder space, which is really just office hours online. So if you do any sort of technical research, these are just kind of open sessions where we answer questions. Again, I won't dwell on this too much, but I myself host the session Tuesdays, 9:30 to 11 a.m. And so if you've got sort of questions pertaining to population research or classical statistics, feel free to browse it. It's open to anyone. Actually, I think it's only open to U of M users. So if you are at University of Michigan, please feel free to join us there and bring questions. So turning toward the workshop itself, I'm pleased to welcome Ryan Walters here today. Just some general notes for the workshop. Like I already mentioned, for those of you here earlier, please keep your audio and video muted by default. If you've got questions, which I'm sure you will, feel free to chat those in. I'll be monitoring the chat. Again, keep in mind that we are recording, so anything weird that you do on video will get captured today, for better or for worse. So just be aware of that. And then I also want to, some of you have reached out about our workshop videos, and we're actually redoing that now, and we'll be hosting things on YouTube. So for those of you that are interested in watching our past videos, I appreciate your interest, and please bear with us as we sort of take off our statistician hats and put on our content creator hats and figure out how to do YouTube. So we're doing that now, and I expect those videos will start to come online in the next week or two. Again, they'll be linked here on our main webpage, so you can pick up the YouTube link here. But yeah, again, just feel free if you're interested in that to reach out to me again. If you have or in the future, please feel free to reach out to me directly, and then or just pick up the link here on the website. So with that said, I'll introduce our speaker today. We're very pleased to welcome Ryan Walters, who's an associate professor at Creighton University within the Department of Clinical Research and Public Health, where he serves as the vice chair for clinical research as well as director of the statistics and informatics team. He's the primary statistician and instructor of research-related courses for faculty and learners throughout the health sciences. And as such, he has extensive experience in all phases of the research process, from study design through publication. Ryan received his PhD in quantitative psychology from the University of Nebraska at Lincoln. His main area of expertise is using the multi-level model to quantify and predict the amount and variability of outcomes from both clustered and longitudinal sampling designs. So again, it's my pleasure to introduce Ryan. I will hand over to him, and welcome aboard. Thank you very much.
Excellent. All right. I'm assuming you can hear me. Yes, the screen switched when I started talking. So let me share my screen here. Okay. Okay. So as Paul mentioned, this course will be applied multi-level models. I'm here in this kind of bitter cold Omaha, Nebraska. Here's my contact information. If you have questions during the workshop, please put them in the chat. If you have questions after the workshop, you obviously can drop me an email here. So the primary point of this workshop is to get you going with estimating and interpreting the multi-level models. I'm very clear that I'm not here to train you as statisticians. So with that in mind, I'm going to present this model with words. I'm going to present it in pictures, and I'm also going to present it with equations. I have full understanding, again, that I'm not training stats people here. So you might be number phobic at some level, and that's okay. You're still going to get an understanding of what the model actually represents. I'm more after appropriate use. As I was editing these slides late into, I guess, early into this morning, I realized that it is a bit ambitious. And so I just want to kind of get you going with the groundwork of these models. We're using one example data set for everything. I've provided code in Stata, SPSS, SAS, and R. I should say that my internet at my work is currently down, so I couldn't remote into that computer, so I can't actively show you SPSS. I do have Stata, SAS, and R on my local machine here at home, but all of the code is provided. All of the code is formatted across software programs identically. The data set is fairly large. I'll put that in air quotes, depending on what type of data you use, but the models that we're going to talk about actually estimate fairly quickly. So feel free to follow along. I will tell you which models do not estimate quickly, and that way you can avoid getting hung up. Although Stata and R tend to stop processes much better than SAS does. In any case, so we'll get to the example here in a minute, and I'll walk through all of that. But the first thing I want to do is kind of introduce the multi-level model. Undoubtedly, many of you know why you're here. You know you have some sort of nested or crossed sampling designs. There's a lot of synonyms for the multi-level model. One of the most common that seems to show up is the generalized linear mixed model, GLMM. It's important to note that I say approximate synonyms because the generalized linear mixed model actually subsumes the multi-level model. The multi-level model is a certain parameterization of the generalized linear mixed model. And we'll dive into this more, but the generalized linear mixed model only becomes a multi-level model when you include fixed effects for every random effect included in the model. There's nothing inherently telling the model that you need to include the fixed effects. But in order to be a multi-level model, they have to have both. And if some of that terminology doesn't make sense to you, I promise you it will. There's really two different types of multi-level models. There's cluster designs and longitudinal designs. We're going to be talking about clustered data only here because that's the example that we have. There's an additional layer of complexity for those longitudinal designs that we're not going to have to cover here because we're not modeling time at all. So we're going to be working with clustered data. In any case, most of what I'm talking about here applies to every single multi-level model, whether longitudinal or clustered, whether conditionally normal response or outcome variable, binary, etc. A lot of it applies directly. So none of this, again, is going to be wasted. There's really two sides of any statistical model. The first is what I call the model for the means. This is going to show up in red font throughout this presentation. This represents the fixed effects. For those of you that don't have any experience with a multi-level model, you may have never heard fixed effect, but the reality is you've estimated fixed effect anytime you've estimated an ANOVA or linear regression model. Those regression slopes are your fixed effects. They're basically what you care about for your hypothesis tests. The other side is the model for the variance. This is going to be our random effects once we talk about those, and then residual. So again, you're likely familiar with residual variance. That's actually the model for the variance in a garden variety linear regression model, there was only one variance component, that's residual variance. It's not directly for most people related to hypothesis tests, but they are what the assumptions are about, because it can actually bleed into your standard errors, p-values, and inferences. And we'll cover that a little bit more here coming up. So anything when we're talking about model for the means is going to be in red font. Anything that we're talking about in terms of the model for the variance is going to be in this kind of blue font here. So there's a number of ways for organizing just statistical models in general. Is your outcome normal or is it not normal? Is it binary? Is it count, etc.? How many dimensions of sampling do you have? One versus multiple? We're going to be living in multiple land. One of the things that I think when folks are learning statistics is they learn the general linear model first, and then they start talking about generalized linear model second, and it's with the introduction of link functions and other response distributions, etc. And I think that's done a little bit of a disservice. So actually, the general linear model, so ANOVA and regression, are subsumed within the generalized linear model. The general linear model uses something called an identity link and a normal response distribution. The identity link is just multiplying the outcome by 1. Once we move into generalized linear mixed models, we're now talking about fixed and random effects. We still have the same link functions, response distributions available, etc. But now we have that random component that's going to capture the nested structures and that excess correlation or dependency. So again, we're going to be talking about multiple sampling dimensions, and we're going to capture those via fixed and random effects. So why are you here? Why do you think you need a multi-level model? The first is it can model dependency across observations. We're going to be talking about clustered data only here. For those of you who do longitudinal data, that data is technically also clustered. You have observations nested within a person, no different than, like our example, we have people nested within states. We can include predictors at any scale, on any scale at any level. So we can have person level and group level predictors. Importantly, these predictor variables are allowing us to actually explain why excess correlation or this dependency exists. We don't just have to control for it. We're actually going to be able to test hypotheses related to it. It does not require the same data structure per group. This is a missing data. This has a little bit of a caveat. We'll talk about this in a little bit. And I can already assure you, you know how to estimate these models. Maybe not so much in terms of the software, but in terms of how to interpret some of the effects that are going to come out of this model. You likely already know how to do this. If you know what the intercept is, right? When all predictor values equal 0, the fixed intercept represents that predicted value. What's the slope? You know, change in the outcome per 1 unit difference or change in the predictor variable. And then what's the variance component? So the residual variance, that the remaining reasons why somebody had a specific outcome value. The variance, residual variance, again, is something that you're looking to explain with your predictor variable. So R square, all of this is going to still exist. It's just going to have a little bit more complexity and nuance, but we're building on things I assure you, you already know. So modeling dependency, basically dependency is a synonym for excess correlation, and the levels of that excess correlation define your levels of random effects. So sampling dimensions can be nested. So again, people within groups. For the example, we're going to have people within states. If you're really thinking through the data structure you have and you cannot figure out a nested structure, it's probably because your data is crossed. This is still within the realm of a multi-level model. So an example of that is kids in neighborhoods who attend different schools. Those kids at level 1 are nested within schools. They're also nested within neighborhoods, but those schools and neighborhoods are cross. They're not mutually exclusive. That would be an example of a cross design. We're not going to talk about cross-sampling designs here, but know that much of what we're talking about is going to relate directly to them. Okay. So dependency is created by a couple for a couple of reasons. The first is just mean differences, constant mean differences across your groups. This is going to be quantified by our random intercept. Do some groups just have, on average, more of the outcome than other groups? The other type of dependency is going to be captured by between group differences in the size of the predictor effect. So we're going to get a predictor effect like a regression slope that's going to apply on average. The question becomes, does that apply equally to every single group. We can capture variability in the size of the effect. Let's say the difference between males and females that could differ between groups. That's going to be tested via something we're going to call random slopes. A much less frequently used source of dependency is going to come from within group correlation, but this is more for longitudinal data because the people that we're talking about at level 1 are considered exchangeable. So you number person 1, you number person 2, but there's nothing stopping you from having person 2 be person 1 and vice versa. Okay, so you're not going to have to worry too much about that. Our focus is going to be on the random intercepts and random slopes. So why do you care about that excess correlation or dependency? Basically, that means you have the wrong model for the variance. The model for the variance, again, dictates the standard errors. Everything we're talking about with standard errors is going to define our basically non-Z sampling distribution. So T, chi-square, F, etc. To the extent you have inappropriate standard errors, your test statistic is going to be wrong, which means the areas and the tails of whatever sampling distribution you're using is now going to be wrong, which means your p-values are going to be wrong. And if your p-values are wrong, undoubtedly, you're going to have bias in your inference. Something is statistically significant or not. That's going to be a problem. You really need to worry about whether you have the correct model for the variance. And with nested data, it means you have to have level 1 residual variance accompanied with level 2 random effect variances. You can include predictors at any level of analysis. So again, ANOVA was about testing mean differences between some sort of discrete groups. If you had continuous covariates, you moved from ANOVA to ANCOVA. ANCOVA is literally just a multiple regression model. So you can test slopes relating to predictors to see if they differ from 0. But if you have a predictor that differs across people at level 1, but can't be categorized into conditions, again, I'm sure most of you know, and I'm hoping most of you do, and I'm not going to soapbox this, but categorizing continuous variables is bad. So if you have a level 1 predictor such as age, creating, quantiles, 10 years here and there, that's just not going to be the way to go. You're going to lose a lot of information there. So if you want to include level 1 predictors in this model, you're going to have to move into a multi-level modeling framework. So let's talk a little bit about those predictors. So there's going to be 2 types we're going to talk about. The first is those that are constant within a level 2 group. So for our example, we're going to have people nested within states. A right to work law for that state is a constant for our study period, which means that every single row of data, every single person within a state is either going to have, yes, that state is a right to work law, or no, it is not. And it's going to be constant for every single person. These are level 2 group level predictors. They are constant or invariant within a group. Where some of this complexity comes in, and we're going to spend a lot of time today talking about, is variables that are not constant within a level 2 group. So these are going to be our person level things: age, biological sex, race, etc. Things that can't be considered constant across the entirety of the state. Some predictors might only be measured at higher levels. So you could have, is the person unemployed, is binary at level 1, or what is the state unemployment rate at level 2. Interactions between levels can also occur. So does the effect of age differ by mid-year unemployment rate? So we have a level 1 person thing interacting with a group thing. I have example code interpretations for these types of what we call cross-level interactions, a level 1 by level 2 interaction effect. I mentioned earlier that it doesn't require the same data structure per group. And that can be seen here in this example data. So we have state ID, which is a constant for each individual state. We're counting the number of people within that state. We have a level 1 predictor that is biological sex. So are you male or not? So 1 equals male, 0 equals female. We have a level 2 predictor of state unemployment, which again, you can see is a constant within each state. And then our outcome is going to be disability. And you can see it ranges, at least in these data, from 0 to 6. Multi-level models, there's kind of this misnomer that they quote unquote handle missing data. They do kind of handle it. They use more information than your garden variety linear regression model, which would be a complete data technique via listwise deletion. But know that missing data is still excluded. It's just what missing data is defined by the row that is actually missing. So Depending on which outcome and predictor variables you decide to include, you could be excluding specific rows of data. So again, let's say our outcome is disability. We have level 1 and a level 2 predictor of biological sex and unemployment. If we're only using male as the predictor, so forgetting about unemployment right now, if we're saying, is there a difference in disability between males and females? We're basically going to be excluding person 4 in state 2. Everyone else has complete data for disability in male. If we're going to use only unemployment in the model, we can see here that we're going to be including states 1 and 2, but we're going to be omitting entire states. So the assumptions we're making about the missing data, I'm not going to dive too deep into this, but because when level 2 predictors are missing, we are excluding that entire level 2 unit. In this case, the entire state would be gone. We're going to have to assume missing completely at random. Of course, these are untestable assumptions technically, but we're going to be working under the assumption that they're missing completely at random. Whereas when we're missing level 1 indicators, we're not deleting entire level 2 units. We're deleting or excluding individuals kind of nested within those level 2 units. We're going to be assuming at level 1, the missing data are at least missing at random. No more is going to be said about that. Missing data is a workshop in and of itself. I don't want to dive too much into that minutia, but just know if you're missing level 2 things, that level 2 unit is going to be gone because again, it is a constant for everybody within that. And then I mentioned earlier, you already know how. So if we take this garden variety linear regression equation, what's the intercept? So the intercept's 150. That's when age and male both equal 0. In this case, if male is 0, we're talking about a female, but if age is 0, we're talking about somebody who's literally just coming into this world. So this really highlights the need to center your predictor variables. We're going to talk a lot about centering. Centering generically for right now just means finding a meaningful 0 point. The effect of a continuous predictor variable, so for every being 1 year older was associated with a 2-unit decrease in body weight. The effect of a categorical predictor, in this case, biological sex was treated as binary, so it's literally a t-test. Males are about 50 pounds heavier on average compared to females. The residual value is going to capture the deviation of what's predicted in this model for the means from what was actually observed. And then the residual variance is going to collect all those residual values and tell you how much remaining variance exists in weight. Is there remaining reason why a specific person had a given body weight? Okay, so that's kind of the overview. Again, I'm assuming I glossed over that fairly quickly. I'm assuming you know, at least we're aware of some of that information because it related to why you're actually here. So let's talk very quickly about some statistical approaches for clustered data. One of the questions that came up when we were putting this workshop together is, I don't really know when we should use a fixed effects approach versus a multi-level model. The choice is you can use either. The purposes of them are very, very different. So you can use either fixed effects approaches or random effects in a multi-level model to quote unquote handle that between group dependency or correlation. Speaking specifically to fixed effects approaches, the way you're going to do this is you're literally going to create n-1, so number of groups at level 2 minus 1 dummy variables. They're going to be binary. Are you in state 1? Yes or no. Are you in state 2? Yes or no. Are you in state 3? Yes or no, and so forth, all the way through to the 50 states. You're going to include 49 of those in the model, with the 50th serving as the reference as fixed effects. So you're going to get 49 separate regression slopes that represent the difference between a given state and the reference state. What this does, it actually controls for sampling and dependency, explains all of the reason why the states are different. So it is an ANOVA type question. Is there a difference in the outcome between states? Period. That's the question it literally answers. Problems. No additional group level predictors can be included. So if you just want to know if there's differences and that's all you're interested in, fixed effects approach is going to be fine. But if you want to know why or what specific state level characteristics at level 2 are associated with those differences, you cannot include additional predictors at the state level in that model, because there is no remaining between group variance. You've already explained all of the reason why the groups differ by specifically identifying the state that they live in. The other thing is, you might see in some textbooks, the fixed effects approach is actually required or recommended if you have less than 10 level 2 units. This is more about precision of the estimation of the random intercept variance from the multi-level model. I say it's kind of mad. There's a lot of issues that go into precision of those level 2 units. If you understand, central limit theorem, bringing it back from undergrad, if you talked about that, they say basically 30 is what you need, but that's a bit simplistic too. So again, if you have a small number of groups, fixed effects might be the only way to go. Remember, you need at least 3 observations to have a meaningful variance. If you have 2 observations, it's your sums of squares. That's not a variance. If you have 3, now you actually have a variance. You, in theory, can estimate a variance component, a random intercept variance in your multi-level model with 3 observations. It's just going to be really imprecise. As the number of groups increase, you're going to have a better estimate of those between kind of group differences via your random effects. So let's just show you really quickly here the example. And then I just want to show you a fixed effects approach. So I included 3 PDFs. There's a lot of redundancy within these PDFs. So again, they're kind of standalone documents as is. We're going to be looking at the example called fixed effects, and we're going to look at, the example itself and then models 1 through 3. So if I open up the fixed effects PDF here, let's talk a little bit about these data. So this is the example that's going to go through the entirety of the workshop. The data are from the 2017 American Community Survey. This link is active. It'll take you there. You can read up on it. We excluded patients, again, I'm in medicine, so that's really how I view this. We excluded respondents younger than 25 and also excluded respondents older than 89. So 90 and older, I wasn't sure if that was a HIPAA issue, but again, we just are working with people between the age of 25 and 89. Technically, these data, the way that they're set up, we have level 1 people nested within public use microdata areas, or PUMAs, nested within states. For this example, though, we're going to ignore PUMA. I did include PUMA, though, in the example data that you'll have. And so if you want to extend these 2-level models to work with 3-level data, you have the ability to do that with these data. It's just we're only going to be talking about 2-level sampling design, people nested within states. Primary outcome is going to be disability. The way that we worked with disability is the American Community Survey asked 6 questions specific to sight, sound, cognition, walking, self-care, and independent living. They're binary. Do you have difficulty with a given, do you have difficulties with sight, yes or no, sound, yes or no, etc. We're going to sum across those. So the range of these is going to be 0 to 6. Technically, this is discrete. Again, there's probably more statistical purists on this. This is for example purposes only. So please, if you want to complain in the chat or after to me directly, please do. I'm very much in support of that. But I will tell you, I'm fully aware that this is a discrete outcome. The other piece is there is a ton of zeros. So for those of you who are familiar with kind of those generalized linear models, this lends itself very nicely actually to a zero inflated Poisson or negative binomial, or a negative binomial or Poisson hurdle model. What I'm going to do though is I'm going to exclude the zeros, and I'm going to look only at disability scores ranging from 1 to 6. Okay, so we're going to answer the second part of this question. The respondents who reported a disability, how many disabilities were reported? Okay. The key points for this, again, example purposes only. Everything we're going to cover will directly apply to a more appropriate statistical model we would estimate on these data. So if you wanted to use like a multi-level Poisson hurdle, everything we're going to talk about for the next 3.5 hours now is going to apply directly to that model as well. So this workshop, again, is going to answer 2 questions. Separate documents address each question. Do states differ in the average reported number of disabilities? This is what we were just talking about earlier, fixed effects only model. The second question is how much of the disability outcome variance is due to between state differences and what state level characteristics explain these differences. Question 2 is going to be answered by the multi-level model that we're going to come back to here very quickly. Starter data set, again, your data includes 400,000 some respondents nested within 50 states. The states are numbered 1 to 51. I believe the Dominican Republic was state number 9. That was excluded. So we're talking about 50 states excluding the Dominican Republic. Median number of responses per state was about 9,500, ranging from 750 to about 40,000. All variables for this example are provided in the starter data set. Okay, I also included a couple extras. So biological sex, we're not going to look at in the example, and state level minimum wage, we're not going to look at in the example for you guys to play around with as well. So you have the potential to estimate 3-level models with these data after this workshop. You also have the potential to kind of play around with some of the other variables to see how they go ahead and are entered and interpreted from that model. The majority of models, again, estimate relatively quickly. So I'm going to run the primary software I'm going to use for this workshop is going to be Stata. Those are what the results are actually presented in. But that doesn't necessarily mean that you can't use your software of choice to follow along. The syntax files for each one of the softwares are basically identical all the way through to do the exact same thing. So if I say fixed effect model 2, no matter which software you're using, you're going to get the exact same syntax to estimate that type of model. I'm going to tell you again when some models take longer to estimate than others. So we can walk through some of the code here. So again, I have Stata code to import the data. I'm labeling my variables. The variables we're going to care about the most here are disability, which is the sum of those 6 disability items. We're going to care about age, so that is respondent age, and we're going to care about unemployment. Okay. Unemployment's technically at the PUMA level. So that's technically kind of this level 2 running underneath here where states are level 3. So we're going to talk about some of the issues from that as well. We're also going to talk about right to work. So binary, that's a state level thing. The first thing we want to do is create state level means. So we're going to basically in Stata, we're going to ask for mean age by state, mean proportion of females by state, so that variable is going to be created for you, and then mean unemployment by state. We're then going to go ahead and center. Again, centering means meaningful 0. So the average age of respondents here was like 63-ish. I just rounded to 65, put it right on that Medicare threshold. And so we're going to take age, and we're going to subtract off 65, which means SM age 65. A 0 value there means 65 years of age. For unemployment, we're going to center it at 2%. So state mean unemployment, so SMUE2 has a 0 value representing 2%. So that's basic code that we're going to look at. In SAS, we're going to do much of the same things, label our variables. Creating those state means is a 2-step process. We have to use proc means first, output the data set, and then merge it back in. Doing the exact same thing we had, we're going to go ahead and center our variables at 65 for age and 2 for unemployment. For SPSS, same type, variable labels. We're going to calculate our state means. Much like Stata, it has a nice single function that will create the state means and merge them back in directly. Variable labels, center. And then in R, which I should say, I'm going to give a shout out to Houston Lester at Ole Miss, who helped me with the R code. I did R for my dissertation. I spent 2 years building a Metropolis Hastings algorithm, and it was probably the worst experience of my life. And so I kind of disowned R for as long as possible. However, I start sweating at night. So this is more about me than you, but I start sweating at night sometimes. As a SAS user, SAS licenses are expensive. R is free. And so if my university says, you know what, we don't want to pay for SAS anymore, I'm going to be stuck with R. So I have to learn it at some point. Houston helped me a lot put together this code. And actually, I learned a lot about the differences and pros and cons of these individual package programs throughout. So again, any issues with the code, I'll take responsibility from that. Know that I'll probably text him and let him know that he messed up. But in any case, We're doing the same thing. Labeling. We're going to calculate our state level means. We're going to merge them back in. I'm sure there's an easier way to do this. He did tell me that there is easier ways to do this, but he wanted to map this onto the SAS code. So we calculate the state level means first and then merge them back in, and then we center and label them as well. I should say foreshadowing, when we get to the multi-level model in R, I'm using the Lemur package. LME4 does exist, and you could use that as well. Lemur hates labels. So I labeled here for your purposes only, but you're going to notice in the R code when we get to the multi-level model that I actually create a new data set that strips the labels because for some reason, Lemur said, I don't know what to do if there's a variable label, which is absurd to me, but it's what happens. Preliminary analysis, so our descriptive statistics, we're going to look at primarily disability, age, school mean age, unemployment, and right to work. We're going to ask for histograms just to take a look, and that's how you would do this in all three of your, all four software programs. Results from Stata are presented here. So again, observations, we have our means. The most common disability is physical activity limitations, which again makes sense given the median age of this sample that we have here. The mean disability score is approximately 2. So on average, respondents are saying that they have about 2 disabilities. You can see that the standard deviation is very close to the mean, which should indicate to you immediately that we have a heavily skewed distribution here. Mean age is 63, state mean age is 63 as expected. Unemployment was about 2-ish%, state mean unemployment again 2-ish%, and 54% of the states were right to work states as well. So here's distributions of our variables. You can see this is our outcome. Big pile of ones, very much discrete again, and fully right skewed as expected from those descriptive statistics. Here are the distributions of the predictor variables we're going to include. Know that these models, much like a linear regression model, make no assumption about the distribution of predictive variables, but they're just here for you all to take a look at. Okay, so question 1, the way that I have all of these models set up that we're going to walk through in the example is I provide the model number, I provide the equation, and then I break down the individual code with text boxes highlighting new things that I add going through. So model 1 is our empty single level model. So again, not accounting for people nested within states. We have a fixed intercept only and a residual. In Stata, we're going to use the mixed procedure, mixed followed by our outcome disability. And then we have a comma defining which options we want to include. Variance, request the variances instead of the standard deviation. We're going to be estimating in residual or restricted maximum likelihood throughout all of this. We're going to come back to that. And then our degrees of freedom method is residual. There's a lot of different denominator degrees of freedom options. I included residual in Stata, SAS, and SPSS here simply because I wanted the output to be as close to similar as possible. R didn't have a residual degrees of freedom method. I think the default is either Satterthwaite or Kenward-Roger. I will tell you that if you start flipping denominator degrees of freedom with these data, I know for a fact SAS just blows up. And I allotted 34 gigabytes on my local machine to SAS, and it still blew up when I put another denominator degrees of freedom. So some of this is just literally for example purposes, I needed to get these data estimated. SAS proc mix, define our data, define method equals REML. Model, we're going to have disability equals because there's nothing after the equal sign. We know we're dealing with an empty or unconditional model. We're going to ask for the solution, so the fixed effects, and then our denominator degrees of freedom. SPSS follows much of the same thing, mixed disability, method equals REML, and then we want to print those fixed effects. When we get to the multi-level model in R, we are going to use Lemur package. Lemur cannot estimate the model without a random component, so I had to kind of move back to GLS. So specifying our data, model equals our outcome, and then tilde 1. This 1 actually represents the fixed intercept. And the method equals REML, and we're going to ask for a summary of that. So our Stata results are provided here. couple things to note right away. The first thing in Stata is we have our log restricted likelihood, which is right here. Okay. We're going to do model comparisons throughout this workshop. And one of the things to remember for both Stata and R is that they give you log likelihoods, not -2 log likelihoods. So for model comparisons, you're actually going to have to multiply this by 2. And so you're going to end up with something that is much bigger and positive. And again, we'll walk through all of that when the time comes. The constant is going to be our fixed intercept. Again, we saw this from our descriptive statistics previously. The average disability score across respondents is about 2. Okay. The other thing to note, I have here p-values for continuous sampling distributions. T is a continuous sampling distribution that never touches the x-axis. P-values cannot be 0. SAS definitely puts p less than 0.0001. SPSS, I think, does the same thing. Never put p equals 0 for a continuous sampling distribution, such as t, chi-square, f, etc. That is not a thing. Okay, so whatever your threshold is, p less than 0.05, or if you want to go p less than 0.001, that's going to be a more correct way to do this. Again, 0 p-values, not a thing. In our random effect parameters, we have our model for the variance. In this case, we only have a residual variance. The residual variance is 1.52. So that's the total variance in our outcome, disability outcome, given that there are no predictors in the model as of yet. So the next thing we're going to do, so this was just a starting point to see where we start, both in terms of the fixed intercept and the residual variance estimate. The next thing we're going to do is actually add these fixed state indicators. So we're going to have 49 additional regression slopes, 50 minus 1, that represent individual states. So Alabama, Alaska, etc., all the way through Wisconsin. The way we add categorical predictors in Stata is by using I or IB last. I think IB last allows you to specify what the reference group is, but then it's .st. So the st variable is our state indicator. Much of this remains the same, still asking for variances, still in REML, still using residual denominator degrees of freedom. What we are going to do, though, is we're actually going to predict the predicted values for each observation based on this model for the means here, based on those 49 regression slopes. After the comma, I have XB. This is going to only ask for predicted values based on fixed effects only. This is going to become more important in a little bit, but know that the code, I have it here just to keep it the same. And then we're going to actually correlate disability with the predicted value. This is going to give us the Pearson correlation that we're then going to square to get our R square. It's the exact same way you would calculate R square from a garden variety linear regression model. We're going to do very much the same things here in proc mixed. We're going to use the class statement to tell SAS that we want to treat states as categorical. And then we're going to output out PM is critical because that's going to use fixed effects only. We're going to name that data set, and we're just going to keep disability and predicted. And then I'm going to rename the predicted value as pred M2, and then I'm going to correlate them and then eventually square them as well. In SPSS, the same thing. The difference here is in SPSS, we specify categorical predictors using by. So disability as our outcome by states telling SPSS to treat state as categorical. We're going to put it as a fixed effect, and then we're going to output our fixed predictors, our predicted effects based only on fixed effects, and name it pred M2, and then correlate it. R, using the GLS package, the only thing we've added is right here. So again, we're going to specify RE level allows us to specify the reference group. Factor ST tells R that we want to treat states as categorical, and we're going to specify the last state as state 51 again as the reference group. Method equals REML. The nice thing about R, again, I'm not going to talk all junk about R. It does have some nice features. We can actually calculate R square directly without actually having to use a calculator or some Excel spreadsheet to calculate it. So we can get our total R square from that. So I have abbreviated output here. You can see that we have each state here all the way state 1 through state 50. Remember, state 51 is the reference group. State 9 is excluded because that was the Dominican Republic. And actually, I don't think that was in our data to begin with. So I didn't exclude it. I think it just was excluded. These fixed effects represent the difference in mean disability between each individual state and state 51. Some of them are statistically significant. Some of them are not. Okay. Our residual variance here was reduced from 1.529 to 1.526. We can calculate our R square as approximately 0.2. So our fixed state indicators explained about 0.2% of the variability in disability scores. Here's the correlation. If we take that correlation that we asked for between disability and the predicted disability score for each respondent and square that, we get right around 0.2. So it's within rounding error there. So whether, again, we calculate it as variance before minus variance after divided by variance before, or square that Pearson correlation between the predicted values and observed value, we're going to end up with approximately the same thing. So this has literally answered one question for us. Are there differences between states? And the answer is undeniably yes. Even from the abbreviated code we see here, the size of these differences is provided, at least relative to state 51 is provided here. The one other thing that I mentioned in the example is once you include those state level indicators, there's nothing left at the state level available to predict. They are going to explain all of the reason why states differ. And just to show you that I'm not lying to you, number one, I'm going to include unemployment and right to work. So I'm going to treat unemployment as continuous, so C dot SMUE in the mixed. And then I'm also going to treat our binary predictors as continuous, going from 0 to 1. That's going to operate very similarly interpretationally to had we treated it as a factor. But in any case, so C dot SMUE2, C dot RTW, I'm adding it on the model statements in SAS, not on the class statements, just on the model statements. In SPSS, we define continuous variables after with. So by is categorical, state is categorical, with is continuous. So unemployment and right to work are going to be treated as continuous, and then I add them to the fixed line. In R, I just add them, so plus unemployment and plus right to work. The big picture of why I'm showing you this is because there's literally nothing left to predict. Again, if you're only interested in between group differences and you want to quantify explicitly between group differences, fixed effect approach is the way to go. If you're interested in actually predicting why states are different, fixed effects approach is not the way to go. You need to use a multi-level model. All right, so that's it for the fixed effects approach. I'm going to close that, go back here. Swap. All right. So fixed effects approach has validity for the purposes that it is used for, understanding the limitations of it, really understanding your research question and what you're trying to get out of those clustered data, critically important. Okay. For those of you who are interested in quantifying and then predicting between group differences, you have to use a multi-level model, builds on ANOVA and regression. So it quantifies those between group differences via random effects. Again, random effects are in that model for the variance. They are just conceptually similar to the residual variance you had from garden variety linear regression. They're just at the state level. So how much of the outcome variance is due to between group differences? You can then start predicting those differences with predictor variables via their fixed effects. And we can include fixed effects at any level of analysis. So we can quantify how much of the variability in outcome is between states. And now, once we have that random effect variance, we can go ahead and predict or explain, reduce that random effect variances using unemployment, using right to work state, or any other state level data you might have available to you. So again, random effects give you that predictable control of that excess correlation, while also providing you with less wrong standard errors, as they should. Okay. So the data requirements for the multi-level model, you have to have multiple outcomes from the same sampling unit. In general, more data is better. More individuals at level 1 are going to give you a better estimate of within group differences. More observations at level 2 are going to give you better estimates of between group differences. So keep that in mind. Just know that there's no point in sampling to something that approaches infinity, because each additional observation is going to provide less and less information. Any measurement scale can be analyzed in the multi-level model for the most part, using appropriate link functions and conditional response distributions. We're going to focus here on a discrete outcome that we're going to call continuous. We're going to work under the assumption that it's conditionally normal when it's not, again, just for example purposes. But everything we're doing here, how to include predictors, how to interpret predictors, are going to apply directly had we used a less wrong model to model the disability outcome. Just in terms of measurement, you can statistically, there's nothing you can do if you have badly measured variables or a really junky research design. So understanding what your outcome is, how it's measured, making sure that it means the exact same thing from person to person, from group to group, right? This is just pure measurement. To the extent you have poor measurement, your statistical model is going to be biased, irrespective of how well you estimate and how appropriately you interpret that model. So again, fancy statistical models cannot save you if your measurement is bad or if your study design is really poor. Okay, there are a lot of fancy statistical models. There's so many of them. It's why I have a job a day to day, is to estimate fancy statistical models. But again, putting your thought up front, if you have the opportunity to actually prospectively collect data, put the thought up front, put all the work in, because to the extent you have something wrong there, your results are going to be biased. There's two levels of in a two-level model, which is what we're talking about here. There's two levels of inference. We have between group relationships. So again, anytime I say between, I'm talking about level 2. I'm talking about group level. These are also called intergroup differences. There's also within group. Anytime you hear within, we're talking about level 1. In this case, it's person level for clustered design. At least this example we're using, it's person level. That's that intra, within group kind of variation. They allow examination of both of these relationships simultaneously, and this is important. So if you look at this figure on the right here, which I stole from UCLA's fantastic stats website, which I'm sure 95% of you are aware of, we have 1, 2, 3, 4, 5, 6 groups. Across groups, we can see on average, the outcome is actually increasing. However, once we account and tell the software program that each group represents a distinct entity, we can actually see that within groups, the effect is actually negative. So you can have, not only can you have different scales of variables at different levels, you can also have different directions of effects at different levels for the same predictor as well. Making sure that you properly identify the nested structure is critically important. Okay, 157. Let's do part 3 here, and then let's go ahead and take a 5-minute break. So we've talked conceptually with a lot of words about what the multi-level model is. Now let's take a look at some pictures coupled with some equations. So this is our garden variety linear regression model. Model for the means just has our regression slopes. We have predictor variable X, predictor variable J, and their interactions. Okay. The reason that we specify, that we use the term fixed versus random, is because fixed effects are assumed to be fixed across all groups in our study, meaning that the regression slope for any given predictor variable, its fixed effect, is going to be assumed to apply equally to every single group in the sample. That's an empirical question that we're going to test with random slopes, but initially those fixed effects, again, assume to apply equally. The model for the variance is one residual for each group. So how far off was the predicted value from what was actually observed? Those residual values, we're going to collect them, and we're going to look at their distribution, and we're going to make assumptions about them. Here, the residual values are assumed to be normally distributed with a mean of 0 and some constant or homoscedastic variance. That's it. So those are your residual assumption. If we take a look at just some leading data for that, If this is our, again, 90-degree rotated histogram, we have our mean value of 89.55. That's going to represent our fixed intercept. That's going to be the mean taken across all observations. If we look at this person down here who provided a value of 32, if their outcome was actually 32, it means the residual was negative 58. It's negative because they're below the mean. In any case, 89.55 is the mean taken across all observations. Every single observation within this distribution has a residual value. So we only focused on this one person with a value of 32. But we're going to find basically, again, the mean. We're going to get the deviation for each one of these observations. We're going to square them. We're going to sum them. And we're going to divide by n-1 to get our residual variance. In this case, it's 228.43. Okay. So again, model for the mean is going to provide a fixed intercept and a residual variance in the model for the variance. That's it. Once we start sprinkling in some within group information, though, things get much more interesting, more complex, yes, but much more interesting. So let's say we have 3 groups, each with 5 people within it. Instead of having observations for group J, now we're going to have our outcome, Y, for person I within group J. This notation maps onto Raudenbush and Breich, more of a seminal text within a multi-level modeling. Know that some other authors might use some different notation as well. But again, I is the person, J is the group. That's going to be standard across the entirety of this workshop. So again, 3 groups with 5 people. We're going to start with our best guess of an observation for all observations taken across all groups. That's going to be our fixed intercept, right? It's the most likely value based on that response distribution. That's going to serve as our fixed intercept. That's our thick red line here. Because we have now people within groups and we're telling the model this, we actually have 2 different deviations. Previously, we had seen that the residual value was a difference between predicted and observed for every single observation. Now we're going to have 2 different types of those errors. In this case, we're going to have deviations between each group's mean, represented by the dashed lines, and the grand mean. So how far off is a group's mean from that fixed intercept? This is going to be called our random intercept. These are conceptually identical to the residual values we had seen earlier. They're just deviations. We're going to collect those deviations and we're going to make assumptions about those deviations. The other thing we have now is the deviation of each individual observation, but it's not anymore. It's not from the grand mean. It's actually from the person's own group mean. So our residual values now do not represent the deviation from the fixed intercept to the observation. They represent the deviation from each observation from their own group's mean. So once we move into a multi-level modeling construct, we have between group differences represented by our random intercept and within group differences represented by our residual values. Okay. Random intercepts are going to be notated by U. U0 is telling you, just like beta 0 was the fixed intercept, U0 is saying we're talking about a random intercept. There's a subscript J because every single group is going to have a random intercept value. So this UO is going to vary by group J. The residual values are specific to deviations for person I in group J. So 2 sources of variation. Okay. Between group differences, again, in this case, just random intercepts represented by UO. We're going to take those random intercepts, collect them, make distributional assumptions about them. The variance of the random effects are going to be notated by tau. So tau squared UO is saying this is the random intercept variance. Our within group differences are still residual values. That's still going to be sigma squared subscript E. So random effects are going to use tau squared. Residual values at level 1 are going to use sigma squared E. If we take a look at data from 6 groups here, if we didn't want to account for the individual within a given group, the residual values again would represent the deviation from what's fixed on average here from each observation within that group. Once we add in group level information, we get the group mean, we get a deviation from average. That's representing our between group effect, in this case, our random intercept, and then our residual values, again, are the deviations of observation from their own group's mean. Okay. We can do that for every single group. So again, multi-level model with a random intercept, 2 sources of variance, constant between group differences based on the deviation of their group's mean from the fixed intercept, and then level 1 within group deviations of the observations from their own group's mean. Again, tau squared UO is our random intercept variance, sigma squared E is our residual variance. Okay. Okay. Let me escape. And why don't we go ahead and take a 5-minute break? We'll come back. Well, I'm central time here, so 1:10. Let's come back at 2:10. And then we'll pick up with intra-class correlation.